Fraunhofer diffraction at double slit. When a plane wavefront of monochromatic light of wavelength lambda that incident on double slit. Here double slit AB and CD are the two slits. BC is the opaque portion or the separation between these two slits. This AB and CD are of equal with the small a and the separation is of with the small b. So when a plane wavefront of monochromatic light of wavelength lambda that incident on the double slit, each slit that diffracts the beam in a direction making an angle theta with the direction of the incident beam. On the screen, the point P that corresponds to the position of central bright maximum. The intensity at point P dash on the screen is obtained by applying the Fraunhofer diffraction theory at a single slit and interference of diffracted waves from the two slits. Here in Fraunhofer double slit diffraction, the plane wavefronts that approaching the two slits AB and CD, when it approaches the two slits, the plane wavefront that approaching the two slits AB and CD, where the waves from these two slits that superimpose together to form interference pattern on the screen. At the same time, the secondary waves from these two slits individually reinforced on one another to form diffraction pattern also. So, the diffraction pattern has to be considered in two parts. First one, interference phenomena due to the secondary waves emanating from the corresponding points of two slits from slit AB and CD. The waves coming from these two slits that interfere or that superimpose together to form constructive as well as destructive interference patterns. And the second one, the diffraction pattern due to secondary waves from the two slits individually. Here we can observe the pattern seen on the screen. Diffraction, that central maxima and secondary minima can be seen. Also the interference maxima and minima, constructive and destructive interference patterns or dark and bright interference fringes can also be seen. The interference patterns are produced due to the superposition of waves from the corresponding points of two slits. To find the interference maxima and minima, we consider a triangle AEC, where sin theta is equal to EC by AC. AC is AB plus BC, that is A small a plus small b. So we get EC equal to A plus B into sin theta. If the path difference is equal to integer multiples of lambda, that corresponds to the maximum intensity. That is the path difference EC. A plus B sin theta n is equal to n lambda, that corresponds to interference maxima or constructive interference. Similarly, if the path difference is equal to odd multiples of lambda by 2, interference minimas are produced or destructive interference patterns are produced. Thus, the path difference EC, A plus B sin theta n is equal to 2n plus 1 into lambda by 2. That is the condition for interference minimum or destructive interference pattern. From this diagram, we can see that inside this central bright maxima of diffraction pattern, interference maxima and minima can be seen. The diffraction maxima and minima are produced due to the superposition of secondary waves from the two slits individually. So the condition for diffraction minima is A sin theta n is equal to n lambda and diffraction maxima is A sin theta n is equal to 2n plus 1 into lambda by 2. This diagram shows the Fraunhofer diffraction pattern, the intensity variation for double slit and single slit. So from this diagram we can see that intensity variation in double slit diffraction, Fraunhofer diffraction, intensity is 4 times that of Fraunhofer single slit diffraction.